Hello everybody, welcome to chapter 4 of particle and nuclear physics. Today we're going to be having a look at the standard model. I'll be introducing some basic concepts that you'll need to get your head round to understand how we're going to treat our particles. So we'll be having a reminder about the particle content of the standard model. What are we actually trying to describe? We'll have a look at the Klein-Gordon equation, and as well the interpretation of some of the solutions of the Klein-Gordon equation, and we interpret them as antimatter. Then we'll be having a look at a very simple example of interaction between two particles by exchanging a third particle, and what that means in terms of potentials of our fundamental forces. And then we'll be using that to understand virtual particles, which hopefully I'll explain clearly to you here. So the idea of virtual particles is something that I really would like you to get familiar with, and please do contact me if you have any misunderstandings or questions about this. Hopefully antimatter is going to be a less difficult concept. So here's our standard model here. Again, we've got just a quick reminder. We've got these 12 fermions here, which are our matter particles. We've got 6 quarks. 3 of them have charge plus 2/3. 3 of them have charge minus 1/3. We've got 6 leptons. 3 of them are unit charge and 3 of them are neutral. And they come in 3 generations each, quite nicely displayed here. But for all of these, we have antileptons and antiquarks as well. So you can sort of double your particle content here. And then we've got our force carriers, our standard model bosons. We've got our 4 spin 1 bosons. We've got the gluon, the massless gluon for the strong force, the massless photon for the electromagnetic force, and our 2 weak bosons, the W and the Z, which are massive for our weak force. And finally, our newcomer to the block is our spin 0 Higgs boson, which isn't a force carrier itself, it's responsible for mass generation, and that's about 125 GeV. So how are we going to approach this understanding a theoretical framework for these particles? We can't use classical mechanics because the particles there are moving too slow. And they're also on a macroscopic scale. If we want to have a look at the microscopic scale, we need to move to quantum mechanics. But then things are moving very fast for these very light particles. They talk about very fundamental particles, and their energy and their momenta is usually much larger than their masses. So we need to bring in special relativity and marry that up with quantum mechanics. So we'll be looking at quantum field theories here to describe the particles and their interactions in the standard model. So what we have for the standard model is actually a collection of theories. We have a collection of 2, depends how you look at it, gauge theories, and these satisfy local gauge invariance. These are all quantum field theories. The first one on the block was electromagnetism. So to describe the electromagnetic force, we have quantum electrodynamics, which for short we call QED. And this was proposed by Feynman and Schwinger and Tomanga in 1948 and won the Nobel Prize in 1965. There's a pattern here with the Nobel Prizes. Then later on, in 1968, Glashow, Weinberg, and Salam unified the electromagnetic and weak forces into one called the electroweak force, which is a really fantastic thing that I'll show you later. They are really one and the same force at high energies. And this won the Nobel Prize in '79. And then finally, for the strong force, we have quantum chromodynamics, chromo for color, which for short we call QCD. This was proposed in '74 by Politzer, Wilczek, and Gross and won the Nobel Prize in 2004. It took a long time because we needed to build the colliders to experimentally verify this. So we'll be having a look at QED, QCD, and electroweak unification in this course. So let's start off with something that's very familiar. Let's start off with the Schrödinger equation. That's something that we know describes the quantum mechanics of particles, but we do need to bring in some relativity here as well. We need some relativistic quantum mechanics. So let's start off with the Schrödinger equation, where we've got the energy operator on some wave function equals the momentum operator squared over 2 times the mass operating on the wave function. So we can put in our energy and momentum operators there, and we can give ourselves some relativistic quantum mechanical description of a particle. However, let's have a good look at this. This is first order in the time derivative and second order in the spatial derivative. It's not Lorentz invariant. For our frames moving at uniform velocity, we want our physics to be the same. And so we need our spatial and time derivatives to be of the same order. So actually the Schrödinger equation cannot describe relativistic particles because it's not Lorentz invariant. We need to build in some Lorentz invariance. So let's move to the Klein-Gordon equation. Let's start off from special relativity instead. So our wonderful relativistic equation we have for a particle, that its energy squared is its momentum squared plus its mass squared. Let's use the energy and momentum operators with this to give us the Klein-Gordon equation. And let's have a look at this. It's second order in our spatial derivatives and it's second order in our time derivatives, which means it's Lorentz invariant. Our physics will be the same for frames moving with uniform velocity. So if we use plane wave solutions here, and instead of our classical energy and momentum expression, we're going to make sure we use our special relativity equation for the energy, momentum, and mass relationships. If we put that in and we derive solutions for the energy states that we can take with the Klein-Gordon equation, we're going to get energy solutions of plus or minus square root p squared plus n squared. But take a look at this. Positive energy, maybe we're quite happy with, but negative energy is maybe something that would raise eyebrows here. How can we have negative energy states? But what we actually find is we need these negative energy solutions. I mean, to form our complete set of eigenstates, but what we find is that they describe antimatter. So our positive energy solutions describe matter, like electrons, and our negative energy solutions describe positrons, the antimatter. So we do need these. Now, Dirac wasn't happy with negative energy solutions. This was before the whole concept of antimatter. So it was something a little bit strange. Now, what he tried to do was avoid these negative energy solutions. And what he did was built his Dirac equation describing fermions, and it's first order in our time derivatives and first order in space derivatives. Remember, the Klein-Gordon was second order in each. Now, you will have a look at this if you go on to the fourth year particle physics course. You'll have a look at this in detail. You don't need to know it now, but we've got these 4x4 matrices with alpha and beta here, and we actually have spinor column vectors for our wave functions here. Now, when we have a look at these states that are allowed, two of the wave functions actually describe the fermion with positive energy, but two of the solutions still have negative energy. So Dirac tried really hard to get around the negative energy solution problem, but still couldn't avoid it. His linear solution still had negative energies. Now, his interpretation of this was that we had a vacuum with all of the negative energy states actually filled. And what we could do is excite an electron from this negative energy C to a positive energy state. And the hole that was left would actually behave like a positive energy, positively charged particle, just like the electron. And this was the proposal that was actually a positively charged partner of the electron, a positron, which was subsequently detected. So this was the start of the idea of antimatter to explain these negative energy solutions. Now, Dirac's equation only works for fermions. It doesn't work for bosons. So what I'm going to show you now is that we actually interpret these negative energy states a bit differently with the concept of antimatter. So let's have a look at our solutions for a negative energy particle traveling backwards in time. So we've got our exponential here with a negative energy solution traveling backwards in time. It looks the same as a positive energy particle traveling forwards in time. So that these negative energy solutions with opposite time direction are actually interpreted as positive energy particles traveling forwards in time that are actually antimatter. So these antiparticles are really important. So then we can go forwards now using positive energy solutions all the way through, which makes more sense to us. It's more physical than negative energy solutions. And this is actually very helpful to understand particle physics. These concepts might be very, very simple to you, but before antimatter, they were not. So let's consider particle-antiparticle annihilation here, electron-positron annihilation. These both collide and annihilate into a photon. And we could also consider something that essentially goes backwards in time, a photon pair producing a positron and electron. And this is something that maybe isn't too much of a crazy thought for you here. So what we can actually have a look at, the quantum numbers that are carried into the vertex by this positron are the same as if it's carrying, as if it's an outgoing electron. So this a positron, I've got an arrow for it here, we interpret as sort of a positive energy electron going forwards in time, and it's the same as a negative energy positron going backwards in time. These quantum numbers carried into this vertex here are the same as the quantum numbers carried out of this vertex here. So your time arrow is very important to understand the negative energy solutions. So let me delve into this a little bit more. Let's consider an electron and a photon interacting. So the electron's going to absorb a photon and then emit it. So we've got two stages here. The electron is going to come in, emit a photon, and that lower energy electron is then going to absorb this photon, and you've got this higher energy electron here. Now, if this vertex here happens first, and this vertex, this is something that we actually cannot probe in nature. All we know is that we send these particles to collide, and this is what we get outwards. So this is kind of a black box to us. So if this vertex happens first before this vertex, the interpretation is very easy and quite straightforward. This photon should be, the emitted photon should be lower energy than the electron, right? This electron can only give off at most a total of its own energy or less. And so the photon that we detect should be lower energy than this electron. However, when we scatter electrons and positrons, we see lots of cases where the photon is higher energy. The emitted photon here is higher energy than the electron that went in. So how do we interpret that? If we have antiparticles, it's very easy, and this is called the Feynman-Stuckelberg interpretation. What actually happened here is that the bottom vertex happened first. Our photon here pair produced an electron and a positron, which annihilated with this electron, giving you that higher energy photon, because we're summing the energies of this electron and this positron here. So we've got pair production first here and then annihilation here. And that's why that photon is higher energy. But without antiparticles, this interpretation is really hard. So without antiparticles, what would have happened is the electron came in here, emitted a photon of higher energy by sending an electron back in time with negative energy to interact with this photon, giving us this electron. So without antiparticles, you would have to view this as the emission here of a negative energy electron traveling backwards in time, which is really hard for our calculations. Instead, we have antiparticles, and this is probably something that you're quite comfortable with already, that actually this to produce a higher energy photon here than this electron, this photon pair produces first, pair producing a particle and an antiparticle, which then we have the annihilation here, giving us the higher energy photon. So maybe not a difficult concept, seeing as that hopefully you're quite familiar with antimatter like positrons right now, and that you can annihilate particles and antiparticles to give you things like photons. But this used to be, this was quite a big revolution, and this was called the Feynman-Stuckelberg interpretation. Okay, so next what we're going to do is have a look at how two particles interact by exchanging another. And this is the whole concept behind fundamental forces. They are messengers, they are carrying the force, they are carrying the information between two other particles. So for example, we could be talking about two electrons or an electron and positron exchanging a photon between them, i.e. the Coulomb force. And let's have a look at this from a very, very fundamental point of view. We've got two particles here, particle 1 and 2, which we're going to fix in space. So they're not moving in space. We're going to call this point R1 and this point R2. So these two original particles are separated in space by this distance. And they're going to interact with one another by exchanging a particle. So at first it's just the two of them. And then we have this intermediate state where particle 1 has emitted a third particle. And that's going to have to travel across space and time to this second particle here to be absorbed. So simply, for example, an electron up here emitting a photon to be absorbed by a positron. And so our final state here is exactly the same as our initial state. Of course, there will be some transfer of energy there. And this transfer of energy is actually quite important. This shift in energy due to this exchanged particle actually, we'll see, sets up a potential between the two. For example, if this was an electron and a positron exchanging a photon, this is setting up a Coulomb force between them. But let's have a look at this from very first principles. I don't care that they're electrons, positrons, or photons, or whatever. Let's just use second order perturbation theory to try and describe this. So this exchanged particle is really important. What its energy and its momentum and its mass is going to govern the energy shift between these states. So we're going to need a second order perturbation theory here. We're going to need the transition matrix here from state I to state J, from when we have 2 to 3 particles, i.e. from when particle 1 emits that third particle. And then we're going to also need to describe the transition from the third particle being absorbed by particle 2 back to just 2 particles. And there's going to be an energy difference between state I and state J. And the larger this difference is, the smaller the overall shift is going to be. It's on the denominator here, so it will bring that down. And what we'll need to do is actually sum over all of the possible states we can have in this intermediate state in terms of their momentum and their energy ranges that they can take. So this transition here, I to J, is going to happen at R1, and this transition down here from J to I is going to happen at point 2 down here, so R1 and R2. We're going to fix those in space. Right, so let's consider our first transition where we're starting with just 2 particles. One of them emits another to give us this state J where we've got 3 particles. So our first wave function for the initial states is just our original 2 particles. And once we've got a third emitted, we've got this 3 particle here traveling through space with particular energy and momentum. Okay, so to understand our transition probability here, we're going to have to integrate this. We've got our original 2 wave functions in our initial state and our final wave functions here. And we're going to introduce a Hamiltonian here with this factor G that will describe the probability of emitting this particle, this third particle, in the first place. And we're also going to need this factor of square root of 2e here, and that's required on dimensional grounds for this Hamiltonian. If you go back to AQP, you will have seen it described and explained when you did the vector potential of a photon. We also have a direct delta function here that will constrain this interaction to happen at R1, so that the emission of this third particle happens here at R1 and at no other point in space. Okay, so this integration is relatively straightforward. We have our factor of g over square root of 2e here, the normalization factor for our emitted third particle here, which propagates through space with some energy and momentum. Now we can do exactly the same thing. So we've just had a look at the transition matrix here for the emission. We can do exactly the same thing here for the absorption of that particle. So this is exactly the same approach. However, here we've got this is happening at point in R2 in space. This absorption happens down here at R2 and the emission happens up here at R1. So now we have our two transition probabilities, and we can pop that into our second order perturbation theory to have a look at that shift in energy. So we've got our factors of g squared over 2e coming from that rough Hamiltonian that we've used. We've got n squared for this normalization of the third wave function. And the propagation of it through space and time depends on its momentum here and how far separated particles 1 and 2 are. The energy difference between I and j is simply going to be the energy of this particle here. So we can simply replace this energy difference with E. So we have our shift in energy with one particle being emitted and that particle then being absorbed. What about this normalization factor here? Now, previously we've had a look at normalizing our wave functions to one particle per box of side L. However, we need to take into account relativity here. Our boxes are going to be contracted by a factor of gamma, which relies on the energy and the mass of the particle. So this Lorentz contraction is going to depend on that energy of the particle that's being exchanged. And so the conventional choice here is to choose a normalization factor that is a square root of 1 over L cubed normally, but we're going to say it's 1 over the square root of E here. Now, normally, when we had a look at these normalization factors, they would have been cancelled in the initial and final states. But because we need to have a look at this intermediate state, there's no such cancellation, and we need to choose this carefully. So let's put all of these pieces together now. We're going to do an integration, as second order perturbation theory suggests, over all of the different final states or intermediate states that are allowed. So we're going to need to integrate over all of the different energies and momenta that are allowed for that exchanged particle. So we're going to need to understand the density of final states for each of those allowed states as well. So we're going to pop in our density of final states here. We have our part from our Hamiltonian here as well. So popping those in, we have our normalization factor squared there, which is 1 over L cubed. We could also write that in terms of energy as well. And then we have our usual factors coming in from the density of final states. Go back to chapter 2 if you don't remember that. So we have an expression now for the energy shift when one particle is emitted and then absorbed by that second particle. You can do this integration if you take your z-axis along the line of sight between the two particles. This is done in Appendix D for you. Please do have a look. And then we can do this integral, which is done by residues, to find this energy shift goes as g squared. Remember that sort of probability that something's going to be emitted or absorbed by those initial two particles. We've got an exponential that goes as minus mr and then over r. So let's take a careful look at this. This energy shift depends on the separation between the original two particles and the mass of the particle that is actually being emitted as well, the one that's being exchanged. So let's have a look at a final stage here. There's usually not just one interaction. Usually two particles are exchanging, for example, an electron and positron are exchanging photons all the time. So let's bounce that same particle back to particle 1. So in state I, this time particle 2 is going to emit the same particle and bounce it back to state I, so that we have actually exactly the same state as we started with. There's been an exchange of, for example, one photon to another and then exchanged back. We will get the same result for the energy shift from 2 to 1 as from 1 to 2. So we can add these together then to get the total shift in the energy exchange, as one particle is exchanged twice between the two particles. This gives us a very famous and very basic potential. This is the Yukawa potential. So this energy shift, have a look at this. It depends on that probability of emission and absorption for that. So that will describe the force, or the sort of intrinsic strength of the force that we're talking about. It describes the mass of the particle that's being exchanged and the range over which it's being exchanged. And it's negative. That energy shift is negative. It's an attractive force between the two particles, and it decreases exponentially with the range, the distance of the two particles that are exchanging it. So just for example, for an electron and a positron exchanging a photon back and forth, an attractive potential is set up, and we have our Coulomb attraction. So here's Hideki Yukawa, who won the 49 Nobel Prize for his work here, for this very simple Yukawa potential that is set up when two particles are exchanging a third. Depends on the mass of that particle. It depends on the separation of those particles and the intrinsic strength of the force itself. So it has a characteristic range. If you're exchanging a massive particle, you'll have some sort of quantum wavelength of that exchange particle that goes as 1 over m. So the more massive the particle that is exchanged, the smaller the range that it acts over. And this is quite important for the weak force, that it actually exchanges W and Z bosons. It restricts the range of that force. But then for massless forces, for massless particles being exchanged, this potential becomes infinite in its range. Very Coulomb-like. This exponential will go to 1. This exponential will just disappear, and we'll just have g squared over 4 pi r. And that looks very Coulomb-like, this 1 over r potential. And in fact, Yukawa used this basic idea of interaction with particle exchange to describe the nuclear strong force. He measured the potential of the nuclear strong force and the range over which it was acting over to determine the particle that was being exchanged. And he determined that a particle of mass about 140 MeV would explain that very nicely. And this was the prediction of the pion, which was subsequently discovered. So when we're talking about interactions between protons and neutrons in a nucleus, they're actually exchanging pions, not gluons, and I'll explain why later. But the pion was predicted and then discovered. So Yukawa won his Nobel Prize for this. So let's have a look at some simple scattering off of this simple Yukawa potential. Some particle is coming in and scattering off of this potential. We can use the Born approximation for the matrix element here with the potential that is described as the Yukawa potential. So we're going to plug that in there. And then we have our matrix element here. You can do this integration along the z-axis again. And we will get our matrix element that simplifies very nicely to g squared, this fundamental sort of strength of the interaction, probability that we have the emission and then the absorption. And then on the denominator, we have the momentum exchange between the initial and final states and the mass of the particle that is exchanged. So this momentum exchange is very important. We write this momentum exchange as Q squared, as the difference between the energy squared and the momentum exchanged. So this Q squared is actually called an invariant mass. It's basically the mass of the particle that is exchanged between the other two. And it's called a virtual mass for a very good reason, in that it can be negative and it can be positive, it can be imaginary, it can take a lot of different values. And the difference between the invariant mass of the particle that it's exchanged and its real mass is very important. It'll basically decrease your matrix element, decrease the likelihood that your exchange will even happen. So this is the very simple description of a matrix element as two particles exchange another. It depends on the fundamental force of that strength of that interaction. It depends on the invariant mass of the particle being exchanged and how far away that is from its real mass. So this is the idea of virtual mass, and I will go through in an example in a couple of slides to really try and hammer this home. So what we've got are forces arising, for example, between an electron and a positron by exchanging unobservable virtual particles. So when an electron and a positron are interacting via the Coulomb force, that attracting force, they're exchanging photons, but not real photons. Not real as in not with mass of 0 photons. They have a virtual mass, which could be positive, negative, imaginary. And they're completely, these particles that are being exchanged are unobservable. They are happening, if we observe them, then they actually become real. Crazy thoughts, and I'll try and explain some of this to you. But the mass of these unseen particles is virtual. And sometimes we call it off-shell mass, i.e. its mass is not equal to that of its rest mass. So for example, we could have a photon being exchanged, which has a virtual mass of -1 GeV, which is different to that real mass of 0 of a photon. The amount how far away that particle is, its virtual mass is, away from the real mass of that particle determines its virtuality. And how virtual a particle is limits its range. So for example, you can have a look at Heisenberg's uncertainty principle for the time or the range that this virtual particle, this exchanged particle, can travel over. And that depends on the difference in its virtual mass to its real mass. It restricts its range. So let's go back to our example of an electron and a positron exchanging virtual photons. Virtual because we can't probe those photons that are being exchanged. But we can see the force, of course, the attractive force between two opposite charges. That photon being exchanged, the range over which it can travel and the time over which it can exist is restricted by how virtual it is, how different its invariant mass is to 0. And it can happen that you can have a sort of tuned interaction with those perfect energies of momentum to just hit a sweet spot where the invariant mass, your virtual mass, is exactly the same as the real mass, and then it can be observed. So we can, I'll show you some of the examples through this course where we're going to tune a collision to create real Z bosons and real W bosons that we can then detect via their decays. Okay, so let's go back to our matrix element here. It's really important that you understand how this is constructed. We have our probability of emission and exchange encapsulated in this G squared, and you can think of it as the strength of the interaction. G itself is called a coupling constant, and we'll see this when we use it in Feynman diagrams. It's different, for example, for the electromagnetic force versus the strong force. It's larger for the strong force. It describes the strength of the force. We have then on the denominator q squared, this virtual mass of the exchange particle based on its energy and momentum, and the real mass of a particle as we actually know it and measure it in nature. And so how far away, how much these differ, actually can decrease our matrix element. And if we hit a sweet spot in our interaction where that exchange particle has energy and momentum equal to that, to give us a mass equal to that of its real physical mass, then our matrix element explodes and our rate of interactions explode. So the g squared here, or g, our coupling constants, are sometimes separated from what's called the propagator, which is 1 over q squared minus m squared. So when you have a look at the matrix elements for any particle exchange, any interaction, you can look at the intrinsic strength of your interaction, as well as the propagator, and try and consider how far off shell mass our exchange particle is to the true physical mass. So for example, if we're exchanging a single photon, with photons have real mass of 0, then our matrix element becomes just g squared over q squared. And so it depends on the strength of that interaction, which is the electromagnetic interaction, and q squared, the invariant mass actually of our interaction. And so the lower that is, the higher our matrix element is, and the higher the rate of our interactions. So when we've got single photon exchange, this rate of exchange actually decreases at higher energies. Right, okay. So let's have an example for this. Let's, and hopefully this will clear things up for you. And I will share example. Right, here we go. I'm going to use virtual particles to explain why a free electron cannot just absorb a photon. So here we're going to have well, let's do it in blue then, a free electron, and we're going to have it absorb a photon. I'm going to show you why this cannot happen in nature. Right, so we're going to draw a diagram where we've got an electron. It's going to start off just at rest, and it's going to absorb some photon. And when an electron absorbs a photon, it remains as an electron. So this is our sort of start of a Feynman diagram about it. Time's going from left to right. An electron is existing in time, absorbs a photon, and basically becomes a higher energy electron, right? So you can kind of imagine our initial state is a electron at rest, and we've got some photon coming in here that way, and then our final state is just an electron, and of course that's going to be given some momentum. Of course, we need to conserve momentum. This photon is going to have some momentum in the final state, in the initial state. Right, so I'm going to label these particles. The photon is going to be particle A. Our initial electron is going to be particle B, and our final state electron is going to be particle C. So I'm going to really, really simplify this. Let's go first to our initial state, where we've got our electron at rest and a photon comes at it, and it's absorbed. Let's have a look at our invariant quantity, our invariant mass in the initial state. I'm going to call it Mi. So we're going to calculate this as the sum of the two energies, the energy of A plus the energy of B, all squared. And we're going to subtract from this the momentum of A plus the momentum of B, all squared. Now, in this initial state that we've had a look at, the energy of the electron is simply its mass. We're going to do it that way. No, first let's have a look at this. EA squared. Let's multiply out our brackets first. Getting ahead of myself. Let's multiply out of our brackets so that we can have some practice here. You may be able to remember a lot of this from the last few lectures. Minus 2 PAPB. Right, so we've got terms here that are the mass of A squared plus the mass of B squared plus 2EAEB minus 2EA, oh, PA, PB. Right. The mass of A is the photon. Photons are massless, so that's 0. And we have set up an initial state where the particle B, our electron, is at rest, so that this term goes to 0 as well. That's quite simple then. We've just got mb squared plus 2EAEB. Right, so the mass of the electron squared plus 2 times the energy of the photon times the energy of our electron, which is actually its mass. Let's go to the final state and work out the same thing. This should be quite simple because we've just got an electron, right? So our final state invariant mass is the energy of c squared minus the momentum of c squared, which should be simply the mass of c squared, just for a single particle. Now we want Lorentz invariance. We need that. We don't want our physics to change. Invariance. That means that our initial state invariant mass should be equal to our final state invariant mass. Let's have a look at that then. Here we've got mb squared plus 2EA EB equals mc squared. Simply that easy. What do we know here? We know that the energy of our photon, EA, has to be larger than 0 for it to even exist. So this term here must be larger than 0. But then we come to a little bit of a quandary, because the mass of B and the mass of C, they're both supposed to be describing the masses of electrons. How can the mass of the electron squared plus some small amount be equal to the mass of the electron squared? So these two are not equal. We do not have Lorentz invariance. Our initial state invariant mass is larger than our final state invariant mass. So we're hitting problems. So this is really, really bad. We need Lorentz invariance. So let's bring in this idea of virtual particles again. What if this final state electron didn't have an invariant mass equal to that of the electron? Let's throw this idea of virtual particles in here. So what if, well, bring in these virtual particles, mc was not equal to the mass of the electron? What if it's virtual? Then we can have mi equals to mf. We can bring in this Lorentz invariance again. So that's great. But what does this mean? This means that this electron that's been created does not have invariant mass of 0.5 MeV, like the one that we started with. It's virtual. This restricts its range. This restricts its lifetime. In fact, something else has to happen. What we find is because we have this, oh, I missed my blackboard now. Let's draw it again down here. We've got this real electron coming in here and this real photon coming in here, giving us this electron which is virtual. Something else has to happen to it. It cannot exist over a very long range or a very long lifetime. Something else has to happen to it, something as simple as emitting a photon to become a real photon and a real electron. So this process by itself here is not a physical process. So this by itself is not a physical process. An electron cannot just absorb a photon and give us a real electron. Something else has to happen. So something else has to happen, like the exchange of another photon or something like that. And then we have a real physical process. And it's now there's a little bit of a side. So if an electron is in a vacuum by itself, it cannot just exchange a photon. It just cannot absorb a photon, and it's the same thinking behind a photon just pair producing an electron and a positron in a vacuum. That cannot happen as well. The electron or the positron ends up being virtual, and you can prove that to yourself in your problem sheet. What has to happen is something else has to happen. For example, this photon, maybe it's exchanged with some matter. So if there's some matter nearby, we have some extra degrees of freedom, and that can happen. Now, you've seen electrons in atoms. Of course, they can just they can absorb a photon. They have internal degrees of freedom that allow them to do that. But an electron in a vacuum cannot just absorb a photon without something else happening. It'll end up emitting a photon as well. And the same reasoning behind a photon cannot pair produce an electron and a positron. Let's have a look at that quickly so that you can have a look. It's the same thinking if you just have a photon existing in a vacuum. This process as well is not physical. You need something else to happen as well. For example, this could exchange a photon with some, I don't know, some nucleus in matter or something like that. That would be a physical process because this intermediate electron would be virtual, or positron, or however you want to do it, would be virtual, and it makes itself real by exchanging another virtual particle with nuclei. So hopefully that is clearer to you now. We basically violate energy and momentum conservation unless we bring in these concepts of virtual particles. And in fact, I mean, maybe you're happy with violating energy and momentum conservation, maybe over for a short time. However, your calculations become incredibly complex because you have to do all of your calculations for all of the different energy and momentum violations that you can consider, which is a huge amount. And instead, we consider virtual particles that have an invariant mass not equal to the physical mass of that particle. So for example, that I gave you here, an electron would be produced with invariant mass not equal to 0.5 MeV. It could be something like 2 GeV, or a negative invariant mass, or an imaginary invariant mass. We do consider all of them, but it does make our calculations a hell of a lot easier. And the whole fact that it's virtual means that it's restricted in space and time. Something else has to happen to it. Right, let's move on. I think we're at the summary. So this lecture has introduced a few concepts that are absolutely core to all of our standard model gauge field theories. We've got our standard model particles, we've got our 12 fermions, our 5-spin 1 bosons, and our 1-spin 0 boson. And these are the ones that we want to describe with our 3 overall gauge field theories, QCD, QED, and our electroweak unification. Now, I hope I showed you that we're going to need relativistic wave equations to properly describe these tiny particles at microscopic scales and moving very quickly. We had a look that the Schrodinger equation doesn't work because it's not Lorentz invariant, but the Klein-Gordon equation is. That works really nicely for bosons, and the Dirac equation for fermions. If you take the 4th year course, you'll be looking into these in far more detail. Now, the negative energy solutions that come out of these equations are not to be worried about. They actually describe antiparticles. They're needed for a natural explanation of the interactions that we see. Then we moved on to describing 2 particles exchanging a third. And we had a look at the energy shift, at what happens when they're exchanging that third particle. And it actually sets up an attractive force between them. And we derived the Yukawa potential, this really simple and basic potential that will describe any 2 particles exchanging a third. And we had a look at these exchange particles, and we did an example here. Their invariant mass does not have to be equal to the physical mass of the particle. So we could exchange a photon that has invariant mass not equal to 0. We could exchange electrons that have invariant mass not equal to half an MeV. And this is quite difficult to get your head around, and I understand. Go back to the example that we had a look at, and also have a look at there's a question on your problem sheet number 2 that will will take you through a photon pair producing an electron and a positron in a vacuum, and have a look at this, the same approach. You're not going to conserve your invariant mass in the initial and final state unless you have a virtual particle, in case one of those doesn't have mass equal to the electron. Okay, so that wraps up our introduction of the standard model. The next one we've got is a sort of crash course hour in how to draw Feynman diagrams. As well as relativistic mechanics, one of the key points of this course is to be able to draw these processes, these Feynman diagrams, which will describe the calculations and the interactions that are going on. So we'll have a crash course hour of that next. Okay, thanks a lot.